Hey OChemStars, this is Mrs. Vandeloy bringing you more OChemStar video. And we continue where we left off from 3.4. We talked about the fact that these double bonds do not rotate. Those pi bonds prohibit that from happening. So what happens that when you have groups off these carbon double bond carbons, they're kind of stuck there. They don't rotate freely. So because they are stuck there, they form an isomer of each other or possible isomer. So here's a good example of 1,2-dichloroethene. Folks, that's not the right name for it, all right? It is not specific enough because both of these structures could be considered 1,2-dichloroethene, and yet they're very different. So notice what these chlorines are. They're on the same side as these carbons. Here, these chlorines are on the opposite side. So I would call this cis 1,2-dichloroethene, and I'll call this trans 1,2-dichloroethene. And so before we really get started here, please write this down. Your key number or your key idea for cis and trans to ever occur is that you must have two hydrogens on the two carbons that form the double bond. You can't have two hydrogens on the same carbon. It has to be one on the one double bond and one on the other carbon of the double bond. So you must have, did you write that down? You must have one hydrogen on each of the carbons and only one hydrogen on each of the carbons, leaving these other things to be the cis or the trans parts, okay? And maybe this will make more sense as we go on. So who cares, okay? Who cares? Well, we do, obviously. So what do we notice is different about these cis and the trans? Well, obviously, their boiling points are different, okay? So it asks, how can these two isomers be separated? It says, obviously, their boiling points. Duh, I gave it to you, right? So it says that the trans will boil off first. All right, so the question now is, why is the boiling point higher for cis and not trans? Okay, well, here's my explanation. The cis can get closer to each other, the larger chlorine groups on the same side. The large chlorine groups in the trans makes it more bulky and harder to get closer to each other. I'll give you a little bit to write that all down. Then I want to show you something, okay? So I'll pause, let you finish writing, and then I'm going to show you a picture. So this is my cis 1,2-dichloroethene, and this is my trans 1,2-dichloroethene. Once again, hey, do you see this trigonal planar that I was telling you about last time? Cool. All right, well, what did I show you here? Imagine these are really large chlorine groups. You can still scrunch these sort of together, all right, by layering them in this way. So these cis 1,2-dichloroethenes can get closer to each other than over here the trans. It's kind of hard, especially if those chlorines are really big, for those trans 1,2-dichloroethene to get close together. So the closer they are to each other, what does that mean? The greater the attraction. So let's go back up again. So I'm hoping this statement now makes a little more sense. The cis can get closer to each other with the larger chlorine groups on the same side. I showed you that picture. The large chlorine groups in the trans makes it more bulky and harder to get those closer to each other. So again, the closer they are, the greater the attraction, the greater maybe the London dispersion attractions, okay? So what? Well, that means it's harder to separate. And it doesn't have to be a chlorine, okay? It doesn't have to be a chlorine, but let me show you something else. If these are chlorine groups, okay, as the problem states, those are one of the big fours. This area is now going to be partially negative, making this area partially positive. All right, and there's going to be that attraction then with that as well. So this partial negative is actually, you know, can get closer to that partial positive. You have a very, what's the word I'm looking for? This is a very symmetric molecule. You really don't have a good partial positive and partial negative section. So you do have somewhat weaker attractions here. So that also comes into play if you're working with a chlorofluoro. But this layering, okay, works if you have large bulky methyl groups or large bulky, any bulky nonpolar groups. Okay, so this is the stacking I want you to really visualize. It just so happens I also use the chloro aspect with the electronegativity as well. All right, let's go back up again. So it says, how do you write both structures using line notation? So that's how I would do it. Again, you don't write the carbons down, you don't write the hydrogens, but you can see the chlorines. You do have to show the chlorine. So here's my cis and here's my trans. Now it says, are the cis and trans isomers possible for one butene? Let's check this out. Well, here's one butene, all right, and notice I try to make it, trigonal planar or whatnot. So I know I didn't put them in. This is a line notation, but how many hydrogens are here? You have 2 hydrogens on the end, don't you? And you actually have one over here as well. Hey, how many hydrogens do you have? You have 1, 2, 3 hydrogens. What did I say at the very beginning? What is the only amount you can have? 1 hydrogen per carbon on the double bond. This has 2. So you can't have cis or trans. There, you don't have to even say that. You don't have to worry about cis or trans on 1 butene. But what about 2 butene? Well, what did I show you here? It looks a lot like the chloros, all right, because here is my trans 2-butene, here is my cis 2-butene. And let's just check out these hydrogens again. How many bonds does this carbon right now show? 1, 2, 3. Oh, so there's a hydrogen here. Yep. How many does this one show? 1, 2, 3. Yes, so there is a hydrogen here. So this carbon has exactly 1 hydrogen. This carbon has exactly 1 hydrogen. Yes, it is possible. Again, 1 hydrogen, 1 hydrogen, same dealio. Okay, they each have 1 hydrogen, so cis and on each carbon, so that cis and trans are possible. Okay, let's go on the next page. So it says problem number 5, which of the following compounds can exist as cis-trans isomers and draw their structures? So go ahead and answer this for yourself. All right, what'd you say for number 1? Here is propene. Okay, so obviously, same thing. No, you don't worry about cis or trans. Why? You don't have exactly 2 hydrogens surrounding the double bond. You have 3. You have 1, 2, 3. Nope, propene doesn't need it. Obviously, my 2 hexenes, all right, work out, correct? So you can see that you have exactly 2 hydrogens surrounding the double bond, all right? Let me show you something about this 3-methyl 3-hexene. So it looks like this could look like trans and this could look like cis, but what's the problem here? All right, you don't have exactly 2 hydrogens surrounding the double bond. You only have 1, and let me use the red to show you that. Whoa, sorry about that. Press the wrong button. Look what you get. Go away. Let's try it again. All right, so yep, I have 1 hydrogen here and 1 hydrogen here. But what I want to show you is this. These are really the same thing, okay? Let me erase this, for heaven's sakes. All right, let me erase this, okay? And I want to show you something else. What if I were to, let's see if I can't do this. Ha, that's pretty funny. Well, this isn't working how I wanted it to. Go away. Let me rotate this one. No, this isn't working. Well, I thought I was going to do something fun, but it doesn't look like I'm going to. So, hey, let's turn it back to where it was. They're the same structure is what I was trying to show you. All right, they have the same structure because we can rotate this. That's what I was trying to show you, is that this is a sigma bond and I can rotate it so it's coming down like this as well. All right, so it doesn't work. It is not cis or trans. So I had said in 3.4, how can I get this double bond to rotate. Do you remember what I said? You got to break a bond, okay? So my first step, all right, this is showing me through either heat or light, I need to break the pi bond. Why does the pi bond break first? Because I had said it is weaker, okay? So again, my goal, I'm sorry, is to go from cis to trans. So the first step is to break this pi bond using heat or light, okay? That's enough energy to break a pi bond, the pi electrons. So what does this look like we're going to do now? These are singleton electrons. This is after I broke the bond, each carbon grabs its original electron. So now what? I only have a sigma bond left, all right? With only a sigma bond, you can rotate. And that's what I'm trying to show you here. So you start with the B's on the bottom, the A's on top, but now you have just the sigma bond. Guess what you can do? You can rotate the sigma bond, okay? So you're going to rotate it 180 degrees. So what ends up happening, let me scroll back up again. What ends up happening is that the A and the B can swap places now. All right. You rotate that 180 degrees. Well, what do you think these two electrons are going to do? That's what's happening here. Those are still 2 pi electrons, all right? They're not being used in the sp2 hybridization. So those two can rebond, all right, making a new pi bond and then forming the trans. So once you have those 2 pi electrons, you can solidify this, if you will, with that pi bond, the double bond, and it will no longer rotate. And now you are stuck in that trans position where you were stuck in the cis position earlier. So let me give you this one more time so you can write it down. And I believe that is it for section 3.5.